Hello everyone, my name is Renuka, Assistant Professor in Department of Electronics and Communication, Maharaja Institute of Technology, Mysore. Yesterday we had studied about the supervisory control and its application and also about the DDC, that is the direct digital control applications, right? So let us just move forward and understand whether DDC is pertaining only for a single loop system, that is a feedback control system, okay, or is it useful for multiple loop within a sequential control. Moving up to DDC applications, we have, if you just look into the block diagram here, we have a general structure of feedback control configuration, okay. So this is the general feedback control system. Why do you call it as feedback? We have discussed this already. When small amount of output is fed back to the input, and there is a controller who keeps in tab the operation of the output that is required, right? So this becomes a controller, right? So in this feedback loop, you have a controller which controls the input that needs to be fed to the processor to get an end entity. We know that, right? So is DDC application only limited for a one single loop system, feedback loop system? No. It need not be. There might be hundreds of loops that we have already studied in one of the examples, where we have more than say about 20,000 loop controls if you just go into the turbine, okay, turbine system, right? And if you just think about just a single feedback loop system, I have already mentioned about an example of washing machine or microwave oven, right? So now, if you just see here, this can be actually explored under three different heads. The first is the inferential, then you have feed forward, and you have adaptive self-tuning control. So what is inferential? Why did this come into being? So now if you just look into this block diagram, you have set points which is given to the controller, okay, and you have a input which is manipulated, and you have the variable. The processor takes all the variable, it does the processing and gives some measured output, okay. So there are certain inputs, okay, there are certain variables wherein you can obtain a measured output, but there are certain variables wherein you don't get the direct measured output, okay. So for which you have to make sure there are derivatives of two or three such action which happens in the controller, okay. For example, if you are talking about a temperature as a measure, so it could be a level of the liquid in a reactor, okay, and the pressure. So liquid pressure as well as the composition in a reactor could become measuring, it is indirect measuring to give a residue of temperature, okay. So if temperature and pressure could be measured, probably the valve or the inlet valve could open, and then probably you can have the solution being fed into a burner, okay. So now you don't get the measures directly. What happens? You get a measure indirectly, okay, by combining action of two or more entities, okay. That is called as a inferential. Inferential is nothing but the derivation of some other measurement which could be predicted, fine. Next you have what is called as a feed forward. Feed forward are usually used in process control systems, and we are going to learn few examples and understand what exactly it means. And adaptive self-tuning control, yes, wherein based on the environmental condition like that of air traffic control system. So based on the external factors, your system can actually predict or monitor or control its action, okay. So how will it adapt itself, okay, or adjust to the external environmental condition away from the controller. So these are the three different heads that we are going to understand about the DDC applications. So the generalized structure of inferential control configuration, as I have told you, if you just see in the previous block diagram here, you just have a processor, it's a single loop, isn't it? And you have unmeasured output. So now this unmeasured output has to be measured, How do we do that? Okay. So we are going for what is called as inferential control configuration. Fine. So here you have the process, you have a controller, you have the input variable, okay. Then you have measured output. This is the usual block diagram, right? So now there are certain inputs wherein input variables that couldn't be measured directly. So for which you need to estimate the value based on certain action that performs in the processor, okay. And that estimation happens in the estimator, and the estimated output, okay, will be given to the controller, and then it will be given to the processor. This is how you are going to estimate, okay. You don't get the output or a measured variable directly, you have to estimate based on the action of couple of variables in a process, then it controls the system, and then it will be sent to the processor for the needful action. So you have unmeasured output which is taken as a controlled variable. So these variables are controlled based on the estimation that we have already made, okay. So that kind of DDC applications are called as your inferential. So let us try to understand with an example as to how we are going to actually study about the inferential. The best example is the distillation column, what you can see here in the block in the picture, okay. So it is called as a manipulated and control variable for a binary distillation column, okay. This is a distillation column, okay. Here this unit, okay, this is called as an accumulator, and this is the picture what you see here, this is called as a reboiler. So you have a reboiler and an accumulator here. So there are basically 4 independent variables. What you can see here is HA. HA is nothing, HA and HB here are nothing but it indicates the level of the liquid in both the accumulator and the reboiler. You can see the level here, right? So this indicates the level HA and HB. XA and XB will always talk about the composition of that liquid which is there in the accumulator and the reboiler, that is on the top and the bottom container here, fine. So now what you can see here is you can estimate the composition here by the kind of pressure that has been built in your distillation tube, okay. Here you have the distillation tube, right. In this column, as and when the temperature increases and it reaches to certain boiling point, what happens? There is a variation in temperature across this region, that is towards your HB and HA, right. So when there is a certain amount of temperature that has been generated or it attains, there is some amount of pressure also built in this volume, correct? This is a pressure. So with this pressure and the temperature, we can estimate the composition of material here in the accumulator and the reboiler, got it? So the contents here could be estimated, okay. The composition here, this chemical composition could be estimated based on the pressure and temperature in the distillation column, okay. So this is an indirect way of deriving the variables, right. So this is how you try to get the pressure of the pressure of the liquid, the pressure of the air which has been fed here, okay. So now the temperature VA, VB and pressure P in the column will give you the composition that could be inferred in accumulator. So this is one of the best example for your inferential control configuration, okay. Next we have what is called as a feed forward control. The second is the feed forward. As I've told you earlier, usually they are implemented in a process industries. So it measures the disturbance of the system. So it measures the disturbance of the system. For example, if there is a process, a distillation process, or you can say bottling process industry, what will happen? There is a sequential operation that needs to be performed. Okay? If there are any variation in the number of units that has been sent, okay, after each and every batches, what will happen? There could be a disturbance or distribution measurement variation could happen during that sequences. That would be calculated. Unlike the previous example where you're going to consider the output, which is a measured output which is derived at the outlet, right? Here we are not talking about the end product, we are talking about what disturbance has occurred in a system and how we are going to measure it. Okay? So, the best example here is the hot rolling of sheet steel. Okay? So, this is a simple block diagram how it looks like. So, if there is any disturbance in the process, okay, because it is a feed forward. So, if there is any disturbances, there is a measurement, and then the measurement is taken care by the controller, and the controller gives that input to the processor, okay, and then you have the measured output, and you have unmeasured output which could be dealt by estimating later. It is not, you are not going to feed it back. It is only feed forward is nothing but only it goes in a unidirection, it is not going back, okay, it is along with the process flow. Okay. So, now if you consider the hot rolling of sheet steel, the initial setting will be usually done accurately, which means that the hot steel, okay, the hot steel which will be initially sent to the rolling mill, okay. If the temperature of those sheets is known to you, what will happen? You will know what could be the initial gap between the two rolling edges, right. If the gap is set according to the temperature of the sheet that you want to derive out. So, at the first stage, if you are accurately designing what is the gap between the two rolling mills, then you can automatically estimate what could be the subsequent gap between the rolling sheets later, right, later stages, so that you can derive a thin sheet, right. So, here usually in a feed forward, the accurate measurement plays a vital role. Okay. If you initially set the gap between the two rolling sheets perfectly, then subsequently you keep on reducing or increasing depending upon your requirement, right. So, doing this, what will happen? The quality of the scrap can be reduced, right. Let us assume that if you are not setting up the right gap between the two rollers for the sheets to be, the sheets to be formed or driven. Okay. So, what do? It just, you will not get an end product of your desired requirement. You will not get the end product correctly, right. So, what happens? The quality of the scrap can be reduced. If you are reducing the scrap, which means you are actually not wasting most of the productive time. Okay. So, the unwanted is the scrap, right. If you reduce that, then the productivity always increases, right. So, doing this feed forward controlling where you can accurately measure the gap at the first stage, then on estimating the rest, okay, you can always derive the kind of sheets that you would like to have, you would like to use in any of the applications, right. So, what is the need? The speed up the process response to the disturbance. Why do we need this feed forward control? Because if you have feed forward control, the speed up the process response. So, as soon as there is a disturbance in the plant, it automatically feed forward controllers. What does it do? It will immediately take an action. So, the response time will be quick. So, when the response time is quick, then you will have speedy operation. Okay. Then you have effect of the disturbances can be predicted accurately. So, if there are disturbances that you know that could happen, that can be predicted accurately only for those systems. That is why we usually use it in process industry, because you know what is the first stage, second stage and the third stage in a plant. Okay, so the disturbance, probable disturbances could be actually accurately calculated, and then you can have the production line set. Okay, this is all about the feed forward control. Then you have what is called as adaptive control. What is an adaptive? We know that we have to adapt ourselves or accustom ourselves to the environment where we stay, correct? The same way here, who is going to adapt? The plant will have to adapt. For example, if it is air traffic control, so the air traffic controller system has to adapt and try to control based on the external factor. Okay, so that is called as adjustment, adjusting the controllers manually or automatically to the environment. Okay, so adaptive control have three most common forms. What are the three common forms? Pre-program adaptive control, that is the first one. The second is self-tuning and model reference adaptive control. So today we will be studying about what is pre-program adaptive control and self-tuning adaptive control. Okay, and the next class we can also study, we can touch base on the model reference adaptive control, because we have PDI controllers there, and we will be dealing about it later. Okay, so now let us look into what is this adaptive control system. So here you have set points. If you just see the block diagram here, you have the set points. It could be temperature, pressure, okay, on, off, logical, in. Okay, so these are the set points which are given to the controllers. Then you have a processor. Okay, then you have a controller output. So the controller output is fed back to the controller in along with the set points, because it has to get adapted. These variables have to get adapted, right? Here this is a main entity, okay, which you actually see in adaptive control. What is that? The processor is connected to the controller through an auxiliary measurement, which will help in the adjustment mechanism of all the parameters that need to be addressed at the input points or the set points. Okay, so if there are any variation in the temperature externally, okay, so then it has to be, the processor will intimate and there will be an adjustment made at the controller, so the set points can be reviewed, okay, reviewed, and then you have the process, then you have the controller and checking the valves condition. Okay, this happens, this is what is called as adaptive, or it is pre-programming. You program for based on the requirement, okay, of that particular plant. Okay, so adaptive or adjustment or preset changes on the basis of change in the auxiliary process of measurement. The example is a reaction vessel that measures level of liquid, or even automatic traffic control, okay, traffic control measuring the air speed. So if you talk about reaction vessel that measures the level of liquid, so if you have a reactor chamber, then you have the level set, the liquid level being set for certain amount. Then if it exceeds that level, okay, because of the exceeding of that limit, there could be variation in temperature in the reaction chamber, right? And that has to be addressed. Fine. So what happened? There is an auxiliary measurement which goes back and tells that the temperature has increased. So the set point is now reset, okay, based on the auxiliary measurements. Fine. So if you're talking about air traffic controller systems, okay, when you have the aeroplanes, landing or taking off, okay, what happens? You always have a speedy airflow. So this speedy airflow could result in a greater velocity, and it might have friction, okay, in the during the travel. So the important aspect is the temperature outside the environment of a that is maintained in an aerodrome, okay, where you have, if you have a bad weather condition, okay, and you might have come across so many scenarios where you have air crashes, okay, and then takeoff and landing is a big challenge nowadays, right? So what is happening? You have to understand the environmental condition. What is the velocity of air that is around the aeroplane when it has been cutting the air in a different way, correct? Because you have a seamless body, so it tries to cut the air through. So what happens? The velocity also changes, okay? So that needs to be addressed here. So that is why we call it as adaptive control. So you are going to, the system or the plant will adapt itself. How do you adapt? You have to write a program for the controller to get adapted by changing the variables and resetting the set points. Fine. Next, and there is an alternative way of explaining the same scenario. If I am talking about the air traffic controller, if you just see this block diagram, the major change here is you still have the set point, you have a controller, you have the processor. Here the disturbance changes in the environment could also hamper the total performance of the plant, right? So alternate approach wherein changes in the external environment are used to select the gain or other control parameters. So measuring external temperature and wind velocity to adjust control parameters. So as I've told you earlier about air traffic control. So if you just see here in adaptive control, we have dealt about what is pre-program adaptive control and you have self-tuning. In this particular block diagram, what you see is nothing but your the completely self-tuning system that which actually an air traffic controller system will adapt itself, okay. So in next class we shall study more about the model reference adaptive control. In model reference adaptive control, usually you have a set references. Whenever we talk about any action, there is some kind of responses. For example, if I am speaking in a different way and if a person who is not able to articulate few words, okay, then how do you measure? There are certain standards that we usually have. For example, the phonemes, if I say A, U and E, okay, those are the sounds, correct, and that has to be aspirated in a particular way, right? If the misarticulation is what, it could A, U, E could be heard in a different way. So those are the voice samples. So those voice samples will be compared with that of the reference, okay. There is a set model where you are going to actually compare. So there is a comparison between the actual and the test samples. The same way we usually have this what is called as adaptive controllers using a model reference adaptive or I can say an adaptive controller with a reference model, okay. This is all about today's class. Thank you for listening.